My name is Chen. I work for OMSIS right now. I have been here for about 1 month, which I enjoyed very much. Today, I think this topic today is not strange to the many of you. Over the last couple of years, there has been a huge amount of information delivered by all different agencies and institutions, including but not limited to the USGS, to the Lower Susquehanna River Watershed Assessment, STAC review on that study, the most recent STAC workshop, which was briefed today very briefly, and also some publications by us at Hopkins. So all of these publications at Hopkins deal with this issue partially or wholly. And today my goal is to give you an overview of the findings from those publications that are particularly relevant to this topic. I want to start with this 2013 publication by John Brady and Ball. As a background, Susquehanna River contributes more than half of freshwater and nutrient loading and sediment loading from the Bay watershed. Near the lower part of this river, there is the so-called Lower Susquehanna River Reservoir System. This system consists of three members: the Lake Clark, Lake Eldred, and Conowingo Reservoir. The Conowingo Reservoir is the most largest member in the system, which has not been filled up effectively, but the two upstream reservoirs have been filled up for many decades. So the goal of that particular study was to quantify the trends for nutrient and sediment at sites above and below the reservoir system, with a particular focus on the comparison of particulate versus dissolved species. In terms of monitoring sites and data sets, near the reservoir system there are three sites. Above the reservoir system there's Marietta and Conestoga, which have been monitored by the Susquehanna River Basin Commission. Below the reservoir system there's Conowingo. At the Conowingo Dam is monitored by USGS. You can see the similarity between the two, between the input and output in terms of the drainage area. So if there's nothing going on in the reservoir system, then we should expect similar or identical trends between the input and output. But I will show you very soon that is not the case. In terms of monitoring data set, each site has been monitored in terms of daily discharge data by the USGS, and then the concentration data have been made available roughly on 26 to 37 sample days per year for different species of nutrient sediment. So there has been a tool developed recently by USGS called WRTDS, which was used to obtain the daily estimates for concentration and loading. To give you a very brief background on WRTDS, basically it uses the daily flow and sparse concentration records, which are typically available at many monitoring sites, as the model input, and give us the daily concentration and loading estimates. This model predicts log concentration as a function of time, discharge, and season, and hence it's called WRTDS. This model builds one single model for each day of estimation. Thereby, it has a unique set of coefficients for each day of estimation. In doing so, it allows the beta coefficient to change flexibly over time, season, and discharge. And thereby, it does not have to make assumptions on fixed concentration discharge relationships. This model has been shown to offer better performance in terms of estimation in a wide range of applications than some of the previous methods. This is an example showing the estimates from the model, the true condition loading and the full normalized loading. I want to draw attention here that the true condition loading is very variable because of the interannual variability in stream flow. But we deem them as the most accurate estimates. If we want to study the downstream impact in terms of ecology, then we need to use the true condition loadings. Otherwise, if we want to assess the management progress, then we need to remove the interannual variability, and hence we need to use the full normalized loading. In this presentation, I will show you the results from both of them. So now let's take a look at the results from that 2013 study. So what have been the full normalized seasonal trends at Conowingo Dam? Remember, this is the output from the reservoir system. Here shows the result for sediment and TP. Each line here represents one season. They have been scaled by the long-term median values. You can see in general there has been a rising trend for sediment in most seasons since around 1995. Similarly, there has been a rising trend in total phosphorus as well in most seasons since around mid-1990s. And this similarity has led us to think that this might be an issue with the particular phosphorus which transport with sediment. And to prove that, we have separately analyzed the trend for particle phosphorus and dissolved phosphorus. We do find that at the Conowingo Dam, particle phosphorus has been trending up since around mid-1990s, similar to the trend for total phosphorus. By contrast, dissolved phosphorus has been generally going down over the record. Clearly, this is the reason behind that total phosphorus rise, which is consistent with the sediment trend. And a frequent question that we have been asked was that, are these trends due to changes in the upstream watershed or due to the reservoir system? To answer that question, we have plotted the trends for normalized loadings for the reservoir input in terms of sum of Marietta and Conestoga stations. You can see that for sediment, phosphorus, particle phosphorus, total nitrogen, and other species not shown here, these trends have been generally downward over the record for most seasons. In other words, the upstream watershed has been generally seeing effective actions in terms of loading reduction. And the trends observed at Conowingo can be largely related to the reservoir effects. And another question we have been asked very frequently was that, are these trends biased by storm flow samples? We don't have consistent storm sampling at upstream and downstream locations or during different storm events. For example, if we have some more frequent events, sampling of storms in the recent period, but not the early period, that might bias our estimates of the loading rise magnitude. To address that question, we have come out two additional scenarios of analysis. The blue points or blue line here represent the scenario based on all samples available. And this orange one was obtained based on all samples but Hurricane Irene, which was surprisingly extreme high concentration for sediment and phosphorus in the record. It should be the highest one in the record. And the purple one here indicates a scenario that we assume there was no storm flow sample collected at all. And you can see this very consistent pattern for input, Marietta sediment and TP. All these three lines, they overlap very nicely. In other words, the storm flow sample really is not making a difference here in terms of reservoir input. And I would say the same for total phosphorus at Conowingo as well. For the sediment here, if we look at the long-term trend, either from the beginning to the end of the record or from the 1995 period, which we think the change or the rise began, this increase it appears to be consistent among the three scenarios. But we do want to highlight that there has been a very dramatic increase during the early 2000s because of the Hurricane Irene sample, that huge 3,680 milligram per liter value. This plot reminds us that the long-term trend is very valid. But if we want to know the year-by-year trend calculation magnitude, then that might be biased by the storm flow samples. Just to be a cautious note on that. Okay. In the follow-up work, we seek to, this was published recently by John Hirsch and Ball, we seek to further quantify the broad long-term changes in reservoir net deposition. Remember that we have reservoir input, we have reservoir output, so we can calculate the mass balance. And to better understand the uncertainties of our statistical analysis, and importantly to quantify the relative importance of the so-called scalar flow events and the moderately high flow events, which we call subscalar levels. So these scalar flow events, which are about 11,000 CMS or 400,000 CFS, have been a major concern because they can deliver a huge amount of materials to the bay within a very short period of time. But they only represent 0.1% of the time in the history. So we want to know for the 99.9%, how does the reservoir functions? How does that reservoir function change over time? And here is the results. We have done 3 different levels of analysis for that particular study. This one is the temporal trends in the CQ relationships, which is based on smoothing curve, which we call Loess. Simply, we apply the data sets, the Martin data sets for sediment, for total phosphorus shown here, as a the log concentration as a function of log discharge. And then we separate the data into 3 different temporal intervals, the green for the earliest one and the red for the latest one. Then we feed the lowest smoothing curve, which is a non-parametric smoothing technique. You can see that this generally increase in the concentration for the red line compared with the other 2 lines. In other words, we have higher concentration for the most recent period for a particular discharge. And that increase in concentration has occurred under a wide range of flow conditions, including those subscalar levels, shown here as the purple line. The purple line here is the scalar threshold. By contrast, Marietta shows this general decline in the concentration for the most recent period compared with the 2 earlier periods. In other words, we have positive progress in terms of reducing the concentration at the Marietta site. The implication here is that this positive progress has not been propagated across the reservoir system to emerge at the dam. In other words, there has been something going on in the reservoir system. And this is a very recent new publication taking a look at the CQ relationships in a different angle. I don't want to go into all the details, but the key contribution here was to extract these beta 2 coefficients from the WRTDS model and use that to give a more realistic and consistent representation of the CQ relationship over time, over season, over discharge. Here shows the result for this beta 2 coefficient extracted from the WRTDS model, showing in color as a function of time and discharge. And a red color means a higher sensitivity or higher dependence of concentration on discharge. You can see if you look at this 5,000 or the 10,000 CMS level, you can see this general increase in the magnitude of these beta 2 coefficients. In other words, at the dam, there has been increasing sensitivity of concentration to discharge. And I want to point out that all this y-axis scale is below the scalar level. So clearly, this shows this dynamics going on in the reservoir below the scalar threshold. Okay, in terms of mass balance, here we have looked at the results based on the true condition estimates from WRTDS. We calculate the input and the output, and then we calculate the net deposition on that scalar. The way we approached this was to use the output-input ratios. Recall that this output-input ratio less than 1, it means net deposition. Above 1, it means net scalar. So for sediment and phosphorus, it was not surprising that they are generally less than 1 because the reservoir was historically effective in terms of trapping of these materials. But you can see this ratio has been going up since around mid-1990s or 2000. And this particular for phosphorus, you can see it's approaching to 1.0. It's getting closer to that. In other words, we see reduced net deposition based on this particular plot. For total nitrogen, the ratio has been stable at 1.0 because it's largely in dissolved form, which is not heavily affected by the reservoir system. Next, we want to quantify the uncertainties around these ratios. To do that, we have focused on this center line of the box plot formed by the annual median of the 365 daily OI ratios. What we did was to run bootstrap analysis using 100 set of representative data sets from the original record. And then we calculated the 100 center lines or the 100 annual medians from that box plots. Then we quantified the mean and the 95% confidence interval for that annual median. You can see that when we zoom into this final resolution, again, this increasing in the ratio is apparent for sediment and total phosphorus. In other words, the reduced net deposition conclusion is robust based on this analysis. In addition, when we zoom into this final resolution, the total nitrogen appears to also have a slight increasing trend in the recent decade, which may indicate an increasingly important role for the particular nitrogen. That's for that analysis. And then are these trends in the OI ratio biased by the differential high flow sampling? We know that these two stations, Marietta and Conowingo, have not been sampled comparatively over time in terms of high flow events. So we have taken a very hard look at the availability of the high flow data sets. We find that during these three big events, there are big difference in terms of high flow sampling. The three events are 1996 Ice Jam, 2004 Hurricane Ivan, and 2011 Tropic Storm Lee. You can see the hydrographs showed here for Conowingo, the outlet station. This is for sediment, but similar for total phosphorus and total nitrogen. It has been sampled quite well in terms of either the rising limb or the peak during the three events. But at Marietta, which is the inlet for the reservoir system, you can see that the peak or the rising limit has been simply missed in terms of high flow sampling. So this may bias our estimate in terms of the output-input ratio analysis. So to remove that complication, we have done a sensitivity analysis in which we remove all those big events samples for both stations. And we find that with this rerun, we found that with these equally sensitive samples, both sediment and phosphorus also again show increasing trend in terms of OI ratio, or in other words, reduced net deposition. The next big question is the OI ratio trend associated with high flow only. To address that, what we did was to simply plot the ratio similar to the previous box plot, but here we break down that into 5 different flow classes based on the ranking at the Conowingo Dam. We find that for each of these different flow classes, ranging from the very low flows all the way to the highest flows, there appears to be an increasing trend in the OI ratio or reduced net deposition. In other words, this loss of trapping performance is not limited to scour flows only. It has occurred on a wide range of flow conditions. We can also look at the flow class which has contributed the most to the massivity rate across the dam. We calculate the relative contribution by each of these 5 flow classes. We find that this Q4, which contains sub-scour high flows, they contribute the most in terms of reservoir input for flow volume, sediment, TP, and TN loading. Similarly, they have contributed the most in terms of flow volume, total phosphorus and total nitrogen loading. But for sediment loading at the reservoir output is the second highest, which may be due to the reason that the sediment estimation during the several big events have been severely overestimated by the WRTDS model. The final piece of analysis here is on the stationary model analysis, where we try to tease out the effect of changing concentration regression surface from WRTDS. This is a typical output from WRTDS showing the estimated concentration for sediment at Conowingo as a function of discharge and time. You can see that the color indicates the log concentration here, and the color or the concentration estimates are not the same between the 1990, between 2000 and 2010. In other words, these concentration estimates have been changing over time. So any interannual comparison of the true condition estimates can be complicated by 2 things. One is the change in the regression surface itself. The other is the change in the annual history of flow within the year of choice. So we want to isolate this part A effect. What we did was to develop 3 stationary models using these 3 different annual surface. What we did was to simply repeat this 1990 surface over the entire PID record to come out this stationary stationary model regression surface. Similarly, we did that for 2000, and then we did that for 2010. And with the 3 different stationary surfaces, we apply the same accurate discharge at Conowingo Dam to get the stationary model estimates. Because we use the same flow discharge history, so any difference among our estimates reflect the difference in part B, or the change in the reservoir function. Next, I want to show you the result on this. We have many different results shown from this study, but here is just one concrete summary on that. What I show here is the prediction of cumulative sediment net deposition in the reservoir system for 3 different years of hydrology, a wet year, an average year, and a dry year. And you can see here the red line indicates this most recent reservoir surface, or the 2010 reservoir condition. And the green line is the 1990 reservoir condition. Comparing these three model results, you can see the red line is always below the other two lines. In other words, for the 3 different years of hydrology, we see reduced net deposition for those years. In addition, the uncertainty from the bootstrap runs indicate that this red envelope is entirely below the blue or the red envelopes. In other words, this is statistically significant for the results. So finally, what's the significance of the Susquehanna trend in terms of the NT-CBW trend? This is a publication that we made in 2015, quantifying the trend from the night rim size on a seasonal basis. We find that here we define NT-CBW as the sum of the night rim rivers. In terms of the annual average loading for the study period from 1979 to 2012, the Susquehanna has contributed about 62% of flow and similar level of total nitrogen. This is not surprising because total nitrogen is mainly in dissolved form. It's not heavily trapped by the reservoir system. For phosphate and sediment, you can see it's slightly below 50% because of the historical retention within the reservoir system. The interesting thing here is that in terms of the NT-CBW total rise in the final decade in our evaluation period, we find that in terms of particular species, Susquehanna has contributed to about 92% of sediment rise bay-wide, but only 68% of total phosphorus rise bay-wide. And this is partially due to that there has been increasing trend in total phosphorus in other parts of the bay watershed as well. In fact, we have separately analyzed the trend for the non-Susquehanna part of the bay watershed, where we find a similar contrast between dissolved species and particular species, with generally downward trend for dissolved species, but increasing trend for particular species. So with that, I want to come out the conclusions. With this statistical analysis of the long-term record, we have found declined reservoir input for both dissolved and particular species, increased reservoir output for particular species at the Conowingo Dam. In addition, decreased net deposition of sediment TP has occurred under a wide range of flow conditions, including subscale levels. Massive delivery across Conowingo Dam has been dominated by moderately high flows. Our conclusions are supported by a series of uncertainty and sensitivity analysis. In terms of future research, we recommended further monitoring and modeling of the reservoir system in terms of loading, nutrient biogeochemistry, its impact on downstream water quality, and also consideration of all these different issues under a wide range of flow conditions. I think many of you are familiar with this. The largest reservoir in the lower Susquehanna River is no longer an effective trap for sediment and phosphorus. It means that the key assumptions behind the TMDL development in 2010 on the part of the reservoir system are no longer valid. So the partnership needs to improve the representation of the reservoir system in the phase 6 watershed model using all pieces of available evidence and information. And the information I have is that in June 2017, the phase 6 model will be released with the incorporated Conowingo new representation. In addition, the partnership needs to evaluate the options to allocate the targets among the different jurisdictions to offset the loadings from the Conowingo. And the EPA will release the final phase 3 WIP targets in December next year. So with that, I would like to make several acknowledgements. My advisor, Bill Ball at Hopkins, and Bob Hirsch from USGS, several collaborators, Damien Brady, Walter Boynton, and Doug Moyer, and also Joel, Gary, and Ken for their comments on the various work, the funding agencies, and USGS and SRBC who collected the data sets. And these publications are available online, and I provide a link in the presentation, which you can download from the STAR meeting webpage. With that, I would like to thank you for your attention and welcome your questions.